To next session. In this session we will solve some questions of strength of material. The topic is column. Question number 1 is a steel column pinned at both ends has a buckling load of 200 kilonewton. If the column is strained against lateral movement at its mid height, its buckling load will be option A 200 kilonewton, option B 283 kilonewton, option C 400 kilonewton, and option D 800 kilonewton. So uh, now the column is pinned at both ends. Okay. Now it is restrained at, if it is restrained at midpoint, then it is also pinned at, it means it is also pinned at midpoint. Okay. So now the length of the column for this part becomes L by 2. Okay. So as for pin end, the critical load is pi square EI by L square. So here L becomes L by 2, and initially it was as critical load was 200 kilonewton. So initially now L dash is L by 2. Now this length is L by 2. So the now new critical load will become 4 pi square EI by L square, because we are putting L is equal to L by 2 for this pin end. Okay. Okay. Now but the pi but the pi square EI by L square is 200 kilonewton. So this new critical load is 4 into 200, 800 kilonewton. Okay. So answer is D. Next, a long structure column length L with both ends hinged is acted upon by an axial compressive load P. The differential equation governing the bending of column is given by EI d square y by dx square is equal to minus Py, where y is the structural lateral deflection and EI is the flexure rigidity. The first critical load on column responsible for its buckling is given by option A pi square EI by L square, option B 2 pi square EI by L square, option C 2 pi square EI L square by pi square EI by L square, option D 4 pi square EI by L square. So the buckling load is given by n pi square EI by L square. So first critical load, it should be n should be 1, so answer is option A. So answer is pi square EI by L square. So first critical load is pi square EI by L square. Next, a column has a rectangular cross section of 10 mm and 10 mm into 20 mm and the length of 1 meter. The slenderness ratio of the column is close to. So to find out the slenderness ratio, we have to find out the minimum moment of inertia. Minimum moment of inertia is 20 into 10 cube by 12. So I minimum is equal to A k square. Okay. And we know that I minimum is equal to A k square, where A is area of cross section and K is minimum radius of the section. Okay. So area I minimum is this quantity and A is 20 into 10. So K square will be 100 by 12, or K is equal to 2.886, or slenderness ratio is L by K, and length is 1000 and divided by 2.886, that is 346. So slenderness ratio is 346. Option B is the right answer. Next, for a long slender column of uniform cross section, the ratio of critical buckling load for the case with both ends clamped to the case with both ends hinged is option A 1, option B 2, option C 4, and option D 8. So the ratio of buckling load for the case when both ends are clamped and and to the case with both ends hinged. So for both ends hinged, the buckling load is pi square EI by L square, and for both ends clamps or picked, the buckling load is 4 pi square EI by L square. So ratio is 4, so answer is 4. Okay. So answer is option C. Next, the ratio of theoretical critical buckling load for a column with fixed ends to the another column that have same dimension, sorry, with the same dimension material, but so this is the same question, so answer is 4. Okay. Next, the buckling load P is equal to PCR for column AB in the figure. As KT approaches infinity, becomes alpha pi square EI by L square. The where alpha is equal to option A 0.25, option B 1, option C 2.0, and option D 4. So this is the figure, and here the torsional stiffness of KT is there, and here the load P is applied, flexibility KT. Okay. So here when the KT approaches infinity, the this this becomes a fixed band, so that there is no slope, no deflection. Okay, so fixed band is defined by that. So there is no slope and no deflection when this KT approaches infinity. So this becomes a one end fixed and other end hinged. So for this critical load is 2 pi square I EI by L square. So answer is alpha is equal to 2.05. Next, cross section of column consisting of two steel strips, each of thickness T and width B, is shown in the figure. The first critical load of the column with perfect bond and without bond between the strips are P and P naught respectively. The ratio of P by P naught is option A 2, option B 4, option C 6, and option D 4. So these are the columns. One is with perfect bond and one is without bond. Okay, we have to find out the ratio of the load. So first of all, taking the without bond condition. Without bond, for each column there will be P naught, that will be proportional to EI, because it is pi square EI by L square. It may be pinned and it may be fixed and it may be any other type of end. But in all the cases, the P naught is directly proportional to EI, or it is 2 EI. And I is or E is same as material is same, so it is proportional to 2 by 12 BTQ. I is minimum motor. So when perfect bond is taken, then P is directly proportional to EI. Okay, and now the this initially the individual for individual column the moment of inertia is BTQ by 12, but now there is only one column with thickness 2T, so the moment of inertia is P into B into 2T cube by 12. So this is P is equal to P directly proportional to E into B 8T cube by 12. So P by P naught is equal to 8 by 2, that is 4. So answer is D.